My name is Don Cornwell, and I am the mission manager for the Lunar Laser Communications Demonstration, which launches in August of this year, and will demonstrate laser communications from the moon back to the Earth at 600 megabits per second, which is a big number. So I'm here for International Pi Day to kind of show at least where pi shows up when we talk about communications and light. I'm going to stick to something very simple here. How many electromagnetic waves can fit into a time period represented by 2 pi? 2 pi is, of course, is a unit that doesn't have length or time or anything like that. It comes from trigonometry. If you have a unit circle, if you know the circumference of the circle, it is equal to 2 pi times r. And r is the radius, like this. So if you set the radius equal to 1, then the circumference all the way around is 2 pi. And so that means that it's the equivalent of 360 degrees, 2 pi radian. Now the next question is, so here we have this unitless angle 2 pi here, and we've scaled this such that this can either be a wavelength if you're considering distance, or it can be a period in time if you're considering time. Okay, so why is this important? So if we pick some arbitrary time and call this a radio wave, that's how NASA communicates now with radio frequency waves. So for radio waves, they operate typically in the gigahertz, which implies that their period, which is 10 followed by 9 zeros in a second. Now we're going to compare the number of waves in a second between radio waves and light waves. If this is one radio wave for one given period, then you would have many, many, many more light waves. And if you look at the ratio of these two, this means that for every one radio wave that you might have in its period, you would actually have 10 to the 5 more light waves than radio. That means that for every radio wave, you have 100,000 light waves. So the question is, why does this matter? It is to understand that data is communicated by sending ones and zeros. We may have a varying bit pattern. So this is a bit pattern, so there's a 1. This is a 0, there's a 1. So there's basically a theorem that says that you need about 10 of these waves to make up any one bit in a certain amount of time. 10 of any given types of waves. So you need 10 radio waves to make up one bit. And what that means for light waves, that means you can make many, many more light pulses. So in summary, we can send 100,000 light bits in the time frame it takes to send one bit by radio. That's why we're using light to send data back from the moon in the LLCD mission. ESC, using pi for the future of space communications. Data from space.